You've tumbled into the Event Horizon with John Michael Godier. In this installment, John chats with Marshall Eubanks. As chief scientist at Space Initiatives Incorporated, Marshall focuses on lunar communications systems and innovative mission ideas for probing interstellar visitors. Earlier, he directed interferometry efforts at NASA's Jet Propulsion Laboratory and the U.S. Naval Observatory, contributing to the guidance and synchronization tech that powers contemporary space missions and GPS. He's the primary author on the latest study, the 3I Atlas, which proposes direct spacecraft missions to a potential remnant from planetary assembly during cosmic noon. Dr. Marshall Eubanks, great to have you return to the show. Actually, I'm not a doctor. Apologies, but I'm no physicist of that caliber, just got a master's degree. Yeah, just so folks know, the one renowned for that was Freeman Dyson. And Bill Ka as well. Yep. Dyson did it deliberately since he wasn't fond of the PhD setup. I could go on for an hour about myself, but I won't bother. Lately, we've spotted what might be the most captivating item in our solar system in ages, perhaps since Oumuamua, or even as far back as Borisov. We can cut Borisov a bit of slack there. But this marks the third verified interstellar visitor we've detected, 3I/Atlas. And it's proving fascinating because, statistically speaking, it could be ancient, way older than our solar system, and hail from the galaxy's thick disk, a region that experienced this wild phase known as cosmic noon. Could you walk us through the concept of cosmic noon? Sure. The notion is that in the galaxy's initial stages, and we're talking really early days, the Milky Way appeared quite distinct. No spiral structure yet, just elevated gas concentrations. And that higher gas level fueled the birth of stars, planets, planetesimals, and objects akin to 3I. That's why it's dubbed cosmic noon. Astronomically, we're eyeing a redshift around 2, so roughly 10 billion years back. Our paper pins it at 9 to 12 billion, but about 10 billion fits. Redshift 2 takes you pretty distant. And observing those eras today involves peering into distant voids at remote galaxies we struggle to resolve clearly. Naturally, we can't directly glimpse our own galaxy from 10 billion years ago, no ancient snapshots on hand. But the prevailing theory holds that when the universe emerged, it was mainly hydrogen and helium, with traces of lithium and perhaps beryllium. Then the earliest stars, those population 3-1s, ignited, forging initial heavier elements, and the process evolved from there. Cosmic noon hit when this build-up was in full swing, you could say, with star creation ramping up dramatically. In stellar nurseries, massive giants and dwarfs alike emerge, but the giants go supernova swiftly. That's their nature, and they disperse the elements they've cooked up. Supernova debris glows brightly, and the rest follows suit. Our solar system likely endured something similar in its infancy, but during cosmic noon, the action was far more vigorous. Models suggest any proto-solar systems born then would average about 300 Kelvin, basically ambient room temp, or slightly chilly for indoors, but akin to Earth's surface conditions. A stark contrast to the frigid realms where stars coalesce nowadays. Plus, element synthesis varies by method and timeline. The Iron Peak group and beyond arise in supernovae from smaller stars or binaries, which demand more time. Consequently, and stellar spectra confirm this, the cosmic noon era showed a scarcity in Iron Peak and super-heavy elements. They simply hadn't accumulated yet. Instead, we spot enhanced alpha elements, built by fusing helium, 4 alpha particles, onto carbon and repeating, like carbon, 12 to oxygen, 16, and so forth. Those dominate relatively, while iron and heavier stuff lag behind. So these compositions stand out, and if you're keen on astrobiology, it's worth pondering how all that might have shaped astrobiology back then. Was astrobiology even feasible with those varied elemental makeups, different ways stars and planets came together? I figure the bottom line is, we honestly have no clue. Sure, there are a few studies out there, but do we truly understand it? Fast forward to what we're observing with Oumuamua. Forgive my shot at the Hawaiian name. The odds of something forming inside a star system, like a comet, asteroid, planetesimal, or whatever, and then getting ejected for some reason. Maybe the star blows up, or two stars brush too close and shake everything up. or just the usual planetary shuffle like what we suspect went down in our own solar system, with young Jupiter and Saturn shifting around, dragging Uranus and Neptune along, and flinging most of those initial asteroids out into the void. Well, all that kind of chaos happens with primordial stuff, and plenty get scattered. But the chance of one such wanderer stumbling into or zipping near another system, say within a handful of astronomical units, is tiny. So, probably, what we're spotting with Oumuamua these days reflects its original condition right after formation. Think of it as a fresh out-of-the-womb infant that's been cruising solo ever since. That said, it doesn't rule out some early drama, like maybe it originated from a smash-up between two worlds or similar. No idea. But chances are, from whatever went down in its infancy, around 10 billion years back, it's been roaming unbound. You might wonder, okay, what makes us say that? The case relies mostly on kinematics, which boils down to stats, nothing definitive, just probabilities. Oumuamua is packing serious speed. That hyperbolic velocity, the pace it held approaching our solar system, untouched by the sun's pull yet, clocks in at 58 kilometers per second. Tough to wrap your head around that zip. It's several times the clip of Voyager, our quickest probe. We're talking roughly 60 times the velocity of a high-speed rifle round. Fast enough to zip across Earth's diameter in about 100 seconds, so the entire globe would whip past in roughly 200 seconds or 3 minutes flat. Insanely quick. And here's another cosmic quirk. It's set to swing by the sun at perihelion on the opposite side from us. No profound explanation, just random chance, like lobbing darts at a board. One might land right, another left. This time, it's veering left while we're off to the right. Earth won't get a front-row seat for this comet's solar close encounter. We'll lean on alternative methods instead, which we'll circle back to. But that blistering speed, combined with its hefty out-of-plane motion relative to the galactic disk, suggests it's no flatliner from the thin disk population. Our sun lounges in that flattened layer, a roughly planar setup spanning maybe 100,000 light-years wide and, statistically speaking, around 1,000 light-years thick. Apologies. Oumuamua's path actually hauls it out to about 1,000 parsecs, or 3,000 light-years. It's venturing farther afield. Of course, that's probabilistic reasoning, akin to suspecting someone near a heist might be involved, not hard evidence. Right now, with a slew of telescope sessions, we're pushing for real confirmation through direct scrutiny. Gathering data and snapping repeated looks feels like the top priority for this thing. Track its changes as it heads sunward and starts altering its emissions. What's especially curious is how its current venting already stands out. Missing iron, say, but showing nickel-based stuff and such. Makes you speculate about a possible shell it could have built up after eons in the interstellar void, bombarded relentlessly by cosmic rays. Now, what ground-based work can we ramp up from this point to squeeze out the most? We want to gather as much information as possible about 3I/Atlas, right? Well, 3I lies pretty much in the ecliptic plane of our solar system, within just 5 degrees of it. It's what we call a retrograde body, meaning it orbits in the reverse direction compared to the planet's motion. But being so close to that plane makes it ideal for studying, and it'll pass quite near the sun as viewed from Earth around its perihelion time. Actually, it approaches the sun about a week prior to perihelion, which is set for October 29th this year. With comets, that's prime time for activity. You anticipate the peak in outbursts, jets, or flares. Take Borisov. It ejected a piece right after perihelion, though it was a tiny chunk, and observers caught sight of it breaking away. Could 3I pull off something similar? Hard to say. Comets are unpredictable, like felines. They act on their own terms and sport tails accordingly. To tackle any observing challenge in astronomy, the go-to solution is simply more data, across wider wavelengths, from more angles, with sharper detail. We crave it all, but resources aren't endless, so it's smart to prioritize. For instance, grabbing spectra would prove invaluable, and shots taken right around perihelion would be especially helpful. As for the crust concept, I'm not entirely convinced. I've come across it in some article, though I can't recall which one. These interstellar visitors likely get battered by meteoroids, much like the moon's surface has been reworked over time. Yet we know next to nothing about the rate of incoming interstellar meteors. No clue on the last impact, or even solid estimates. Statistically, we're in the dark. It might have taken a hit just yesterday, for all we know. So perhaps a crust could form, or maybe it's more like the moon's regolith, a jumbled mix without true crust properties. Or who knows? Every asteroid we've examined shows such variety in its outer layer. I'd bet on unexpected findings. Surprises indeed. You brought up Borisov shedding that fragment, probably heading outbound now, just like the comet itself. The notion of a comet's trail or tail got me thinking. We spot meteor showers like the Perseids, many stemming from old comet paths. Often, we can trace them to a specific comet that's still active. Might we examine any remnants or trail that 3I leaves as it swings away? Absolutely, I believe so. Those meteor showers you mentioned tie to periodic comets that loop back repeatedly, dropping material along the way. Basically, three main types of ejecta emerge. Gases first. Think surface ices like water turning to vapor via sublimation, or dry ice as CO2, even carbon monoxide behaving similarly. Solar ultraviolet light ionizes them into plasma, forming that classic straight tail you see on comets. It's often the most prominent and luminous part, giving those iconic images of a comet with a sleek, extended streak. That's pure ionized gas. Should a spacecraft pass through it? And we'll touch on that possibility. You detect the gases, electromagnetic fields, and such. But it won't spark a meteor display. Those are ions or molecules, not solids. Back during Halley's Comet era, folks panicked over traces of phosgene and toxins, fearing suffocation in the tail. Nonsense. It's an exquisite vacuum overall. The glow is just visible over vast distances due to sheer volume. Then there's the dust, fine particles, roughly the size of fine ash from a cigarette, though fewer folks smoke these days, or that light powder collecting on shelves, behind appliances like clocks. This dust gets pushed by sunlight's radiation pressure and it drifts out of the orbital path, creating what's usually a bent tail, and from what I understand, we're spotting both kinds with Atlas at the moment. Not exactly 3 Atlas, though. I'm no hands-on observer. I haven't been out there recording these sightings myself, but that's the buzz I'm hearing. Plus, there's some coloration showing up, which is pretty intriguing. Then you've got the bigger particles. Picture this. You're warming up icy water or frozen CO2 or similar, and it starts spewing jets. If there are small stones or chunks floating nearby, with such weak gravity pulling them, those can get ejected too, and the comet ends up shedding them. They stick close to the comet's orbital route, dispersing along the mean anomaly. These bits move slowly since they're hefty and barely budge under solar radiation pressure or other forces. Over time, they accumulate, and that's likely behind most meteor showers. There could be slightly larger pieces, like boulders, that break loose too, leading to the odd big meteor. But that's the general concept. We aren't anticipating that from 3-2. That said, the dust tail, the arched one, we should definitely observe. I've checked out some images from yesterday or the day before. The tail's developing, stretching to about 2 arc minutes in length now. Both the dust tail and the plasma tail are visible, and they're expected to lengthen further. We can't forecast precisely how much, of course, but monitoring that's a key goal. No comet showers on the immediate horizon, but it's highly likely that 3I/Atlas is dropping material as it moves, maybe even pebble-sized or bigger chunks ahead or behind. The issue is, Earth won't cross or skim that orbit anytime soon. Interestingly, Mars just went through the zone where 3I/Borisov, or wherever 3I is headed, passed by roughly a week back. It won't loop through again for a full Martian year, and by then, anything 3I left would be scattered far away. Still, it's not all hopeless. As I noted, 3I might have collided with interstellar meteors over eons, flinging off debris, not from heat, but impacts across billions of years. So, it ought to be enveloped in a debris halo. We're short on details about this mechanism right now. No solid data on densities or such. But that opens the door for potential meteor activity on Mars, Earth, or even the Moon if the pieces are substantial enough. That could unfold, and for our planet, it's slated for December, as detailed in the paper. The Mars rovers might catch sight of them too. Unsure if observations are scheduled, but it's feasible. They'd streak from a specific radiant, as in typical showers. We know its spot. Right ascension 19 hours, declination -19 degrees. The origin point where 3I seem to emerge. On Earth, If you're watching, I'd bet the activity would be sparse, nothing like one every minute, or even guaranteed more than a couple per night. But this is prime for amateur meteor spotters to step up. They can't zip to Mars, but they can stake out earthly sights and hunt for these streaks. Even a single or pair of detections wouldn't clinch it. Stats will tell the tale. One vague match from the radiant proves zilch, but several aligning from there? That'd point straight to 3i. Pros running all-sky cameras that scan nightly. Who knows the odds? Could be slim to none, or maybe it'll stand out and lots of folks notice. I suspect it'll pop up sporadically, though. Ground-based watchers have a real shot to contribute there. Maybe now's the moment to shift gears to the broader picture. Or actually, let's pivot to space ops. Let's discuss spacecraft and what's feasible up there. We're in a prime spot to catch that dust trail left by 3i/Atlas using any tools available. Absolutely. Just to get a closer glance. Earth isn't so fortunate in this setup. Our planet's positioned on the unfavorable edge of the solar system. There's simply no way around it. As I mentioned earlier, had 3i swung by 6 months sooner or later, we'd have had an ideal vantage point. But that's not the case, and neither are we. On the brighter side, though, fortune smiles on us because several probes are situated on the advantageous part of the solar system, the 3i facing region, so to speak. And that's genuinely a stroke of luck. Consider the missions at Mars, for instance. Then there's the JUICE probe, which recently pulled off a gravity slingshot around Venus on August 31st. Wait, no, actually at Earth, heading toward another assist, and ultimately bound for Jupiter. Don't forget the Europa Clipper, plus Lucy and Hera, and the Psyche mission en route to its namesake asteroid. All these vehicles are conveniently clustered in that solar system sector. It's not inevitable, mind you. Depending on orbital timings, Mars could be huddled near Earth during opposition, staying on our side. Everything orbits dynamically, of course. But right now, a solid lineup of deep spacecraft is over there. So, 3i popped up in early July, spotted on the 1st. By the 2nd, it was zipping along at incredible speed. We quickly pegged it as interstellar. This was smack in the middle of a U.S. holiday stretch, coinciding with my birthday on the 3rd, and it took until maybe the 4th or 5th for it to sink in. Yep, it's a comet, heading to the far side from Earth's view, which means lousy odds for ground-based looks, but prime for spacecraft. It struck me that we ought to investigate. We, meaning my outfit space initiatives, along with the I-4 is Institute and the Initiative for Interstellar Studies, the American and British counterparts. We figured we'd assess what these probes could achieve. It didn't take long to determine that imaging opportunities lay with Psyche, the Mars-orbiting fleet. There's a whole fleet up there, and JUICE. JUICE isn't super near 3i's path yet, since it's angling outward post-Venus boost, but it'll align eventually. Mars assets will have the nearest pass. Psyche's came on September 4th. The Mars group gets closest October 3rd, and JUICE on November 4th. I began reaching out, nudging mission teams, and I wasn't alone. Plenty of folks were doing the same, especially zeroing in on Mars for that early October flyby. But you have to build the argument. So in the paper we put together, I pushed that this could be a thick disk interloper, carrying specific traits worth hunting, which warrants redirecting probe resources to spot them. And let me say, various mission crews have poured intense effort into this over the past month or so. It's no small feat, far from casually snapping a photo like you're cruising past a landmark on a city bus. This is managing intricate setups light years distant, untouchable and unfixable if something glitches. You handle them with utmost care, and then someone like me pipes up, "Hey, shake things up a bit." That's a real challenge. I tip my hat to those teams. They've been grinding away. Fingers crossed they snag the data. In some instances, it's unclear if it'll even pan out, but they're giving it their all. Key windows hit in early October for Mars probes and early November for JUICE, specifically November 2nd through 25th, for grabbing pics and readings of 3i. It'd be fantastic if ground observers, pros and amateurs alike with their scopes, coordinated efforts during those times for sync data. Plenty of folks on Earth have the gear to join in. I can't really speculate on exactly what folks might manage or not, but I'm confident that plenty of amateur astronomers will attempt to capture sightings of the comet's tail and such when it's perilously near the sun. And honestly, I believe they ought to give it a shot. Any observations they snag during that window could prove incredibly valuable. Naturally, there are a couple more aspects involving space probes, and I'll outline them roughly in the sequence we typically discuss. I refer to them as solar probes, though they're more precisely solar observatories and dedicated solar expeditions. We have two key solar missions, Solar Orbiter and Parker Solar Probe. Plus, there's a fleet of satellites, some circling Earth, others stationed at Lagrange points or in various orbits, that regularly photograph the sun. Those instruments face no issues snapping shots of objects hugging the sun, since their optics are built for just that. The real uncertainty is whether they can spot 3I, which hinges on its size and luminosity. Prospects seem promising so far. That said, we anticipate the recently deployed Punch satellite constellation, orbiting Earth, will likely monitor it and even pick it up. All of them should get a chance to view it as it crosses their sightlines. The key issue remains. Will they detect it? To be precise, that's not entirely accurate. It won't enter Stereo A's field of view, so Stereo A probably can't even attempt an observation. But even if it could, would 3I shine brightly enough or appear large enough to notice? We simply don't have answers yet. Fortunately, there's a dedicated group of enthusiasts who scrutinize images from these satellites, and they'll undoubtedly alert us if they spot anything. No question about it. If ramping up their monitoring is necessary, they should absolutely do so. That kind of information would be invaluable, offering potentially daily updates. It'd fill in the gaps when ground-based views from Earth are blocked, providing a steady chronicle of the action. In contrast, the deep space probes won't deliver continuous coverage. They'll scan for a stretch, then shift to other tasks, and revisit later. So their data will come in bursts. Still, that intermittent insight strikes me as worthwhile. Finally, it appears there's a shot that the Europa Clipper, Hera, and Lucy missions might traverse 3I's tail. The plasma tail seems the most feasible target. They could slice through the plasma tail and perhaps graze the dust tail shortly after, given how the dust curves due to gravitational influences. No probe will plunge into the orbital path to encounter the so-called meteor shower tail, or the neutral tail, as some term it, that 3I is shedding. We lack assets positioned correctly for that. However, there's solid potential for Europa Clipper and likely Hera as well, since they're conveniently proximate by sheer coincidence to both encounter the tail. Another opportunity arises around the first week of November, though forecasting comet tails is tricky. At that point, it's still solar proximate, but any observations from amateurs or others of the tail then would be fantastic for gauging developments. Keep in mind, the tails folks photograph are the visible ones. Yet the ejected material, be it plasma or dust, doesn't simply disappear when it thins out beyond visibility. It persists, streaming outward from the comet. I reckon these probes won't intersect the observable tail. After all, the visible portion probably won't stretch a full $1. Europa Clipper, for instance, will be about $1–2 distant. It'd be fantastic if it did extend that far, but I doubt it. That said, the unseen material endures, including the plasma. Their plasma sensors could detect it and reveal details about the composition. That would be extraordinarily exciting, especially if they brush the dust tail. We're still analyzing that scenario, and sampling it that way could yield fascinating results. I'm unsure how feasible it truly is or if it'll pan out, but we're pushing forward diligently to assess it. In fact, that's our current focus, and to that end, we've looped in some European partners, broadening our collaboration slightly. On a related note about Europe, we're thrilled by the recent ESA update confirming that Mars Odyssey, along with Mars Express and the ExoMars Trace Gas Orbiter, are set to we're gearing up for some observations here. It's underway. Things are kicking off. Absolutely. And we're in the dark about the Hope probe from the UAE or the Tianwen-1 mission out of China. I've reached out to folks involved with both to gauge their interest in monitoring the event and to urge them to join in with their own data collection. Sadly, responses have been pretty sparse. You know, there might be some geopolitical hurdles at play. I won't dive into that. But shifting to tails, we're seeing dual tails in images of various comets, including stunning shots from amateur astronomers of ones like Hale-Bopp. Remember that back in the 90s? Incredible sight. I snapped photos of it myself. I spotted it without any telescope. Same here. Oh yeah, totally. You just step outside, glance up, and there it was, plain as day. I kept my eyes on it for nights. Actually, I recall heading to an opera performance in DC and catching sight of it right by the Kennedy Center, visible to the naked eye. Blew me away. I tilted my head back and boom, it appeared. Exactly. I was tracking it from St. Louis at the time, and yeah, the city's light pollution was noticeable, though it's worse these days. Still, it shone through. I'd head out nightly to check it, but I'd also venture to darker sites for extended exposure shots. I've held on to those images. Someday I'll dig them out. The key point is, in those old comet photos, you can often spot the twin tails clearly, either in the shots or sometimes even live. You notice the ion tail curving gracefully, and then the dust tail stretching straight out. This is visible to the eye in some cases, though likely not with C/2019 Y4 Atlas. And that's precisely what triggers those occasional anti-tails, where it seems like a tail's leading the comet. It's all about the viewing angle. The dust tail comes into play, and with the right geometry, it creates that illusion. That's a sharp observation, especially since Atlas is revealing a couple of anti-tail varieties. One stems from uneven heating that propels gases ahead, like what's occurring with Atlas now, which strikes me as a genuine anti-tail. The other is just optical trickery, not a real anti-tail. It's how you're positioned relative to the orbit, making the path look like a forward-pointing feature. Spot on. Exactly. So, I aim to highlight that there are two distinct mechanisms at work. Comets pull this off in both fashions, and neither is all that uncommon. There's been plenty of buzz around the anti-tail on Atlas, but honestly, it's not out of the ordinary, is it? Honestly, nothing I've observed with Atlas stands out as weird, aside from the chemical quirks to an extent. From what I see, its behavior as a comet is straightforward. Now, that's not my core specialty, but I've been deep in this field for years, and it all feels routine to me, like with 2I/Borisov. Again, setting aside the composition, they both sported tails, activated when expected, and followed the usual patterns. Feels the same to me. I thought, okay, it's ramping up right on schedule, expelling CO and the like as these bodies typically do. But the composition angle is fascinating because we're now building a chemical snapshot. You can juxtapose it against bodies that appear to hail from varying eras. C/2019 Y4, Atlas, and Borisov, for instance, were thought to differ vastly in age. Right? We figured 2I was relatively fresh. And naturally, we lacked a proper spectrum from 2I. No solid data on its makeup, just educated guesses. The sole detection was HCN, which you'd anticipate from interstellar dust. Yeah, that's more of a basic signature, not revealing the full makeup. Like, HCN suggests exposure to rays, but doesn't spell out the origins. Nope, it points to cosmic ray impacts in space. Still, Marshall, the composition puzzle is arguably the most intriguing aspect, as it's exhibiting a few odd chemical traits. Could be tied to its age, or maybe some journey through a unique region that altered it, making the profile unusual. Low CO levels, scant iron, that's baffling. Stuff like that. How can we decode it via the probes and Earth-based telescopes to profile the body? From the probe perspective, tools on the Mars Orbiters and Dixie mission can probe the ultraviolet range, so you can spot those spectral features I mentioned earlier, like the shortage of iron and the abundance of nickel. But just to clarify, that doesn't necessarily point to the iron peak reduction I discussed, since nickel counts as an iron peak element too. We'd anticipate both dropping off together. Plus, the chemical makeup here seems quite distinct. That said, keep in mind that older comets, say the one from 1965, approached the sun so closely that iron and similar stuff showed up in spectra purely from ionization. The material melted and turned to gas, producing vaporized iron lines. That's intensely hot stuff. It genuinely shocked the scientific crowd back then. Now, it's intriguing that none of these recent comets reveal iron or nickel, yet nickel appears more common even far out, several AU away from the sun, where temperatures aren't extreme. There's simply no chance the iron on the comet is evaporating. At 2I/Borisov right now, or any time on its solar orbit, it doesn't get near enough. It swings in a bit closer than Mars distance, but Mars is chilly by any measure. This remains a puzzle, really. The prevailing view is that some volatile compound carries nickel, and perhaps iron too, and these get released as vapor on the comet's surface. Then, solar ultraviolet radiation breaks them apart, freeing the nickel or iron for detection. That theory holds water. Still, I'm not entirely confident we've nailed it down, especially regarding why those compounds sit on the exterior. Is there an underlying cause? Something more profound? Or just random chance? Regrettably, this won't resolve questions about whether it's an alpha element-heavy comet from the outset. If it originated in the thick disk, it ought to be dominated by alpha elements. Those include carbon and oxygen, which are plentiful. You've got water ice, CO, and CO2 everywhere. In fact, from a chemical standpoint, I'd argue against supervolatiles being present. Models suggest cosmic high-noon star formation occurred in scorching zones, with explosive rates packed tightly, akin to the Tarantula Nebula in the Magellanic Clouds, but amplified, far wilder than the Orion Nebula region most folks have glimpsed at night. And way hotter. One study even proposed temperatures hitting 300 Kelvin, above room temp, beyond water's melting point, and well past its boiling. That seems implausible to me. What we observe is heaps of CO2, decent water amounts, but less CO. That's unexpected. It immediately indicates a warm origin, either from an early phase in a solar system nearer its star, or a hot star-forming zone as foretold. Since our predictions aligned with a warm setting, I'd call that a point in our favor. But probably around 100 K, warmer than interstellar voids, sure, but not scorching. You'd expect CO to dominate over CO2, as carbon monoxide is highly volatile and sublimes first. Yet I see little evidence of it. As I noted before, this is preliminary science, driven by initial announcements. Everything could shift once full papers emerge, followed by critiques and deeper analysis. That's my current take, though we surely need additional data to confirm. I'm optimistic we'll gather it when the comet emerges from solar glare. Every observatory has its minimum safe angle from the sun. For Hubble, it's about 55 degrees either side, so quite restrictive. It likely won't observe 2I/Borisov again until December. Webb's exclusion zone began in August and runs through late December. So now we're relying on ground-based scopes and space ones farther out. Haven't heard updates from ALMA yet. ALMA could detect certain molecular signatures higher up in the hundreds of gigahertz range. I'm eager to hear ALMA's take on this discovery. Plenty of folks are likely scheming ways to leverage ALMA for observations. It turns out ALMA can scan as low as 15 degrees above the horizon, away from the sun's glare, which limits its blackout to roughly 10 days or 2 weeks for eyeing that target. Meanwhile, certain scopes aboard interplanetary probes, particularly those on JUICE and various Mars ventures like MAVEN plus the HOPE orbiter, pack the suitable gear to potentially shed light on the situation. There's another compound I'm dying for someone to spot so we can dig into its story: PAHs, or polycyclic aromatic hydrocarbons. PAHs are a mouthful for me, and they're among those enigmas that keep astronomers scratching their heads. Back in the day, space-based infrared spectra picked up these unexplained lines. No one had a clue what they meant. If you're familiar with a benzene ring, picture carbon atoms linked in a cycle. PAHs essentially fuse multiple benzene rings into bigger structures. So, imagine clusters of those rings, and they vibrate in all sorts of ways. The rings compress, or parts bulge in and out since the structure stays planar. It's reminiscent of some bizarre instrument, like a drum crafted from interlocking metal hoops. All those vibration patterns act like drum resonances, but instead of audible tones, they emit infrared spectral features. Same underlying physics, really. We're spotting these pH signatures in spectra, and for ages, their origins stumped everyone. They appeared so arcane, especially those prominent lines stretching into the higher infrared, up to around 13 microns. These days, we've unraveled quite a bit, and it looks like PAHs lock up a huge chunk of the universe's carbon, though not in the sense that you'll stumble on them littering Mars's ground. Nah, this is about interstellar gas clouds, where this material floats abundantly. It's everywhere out there, showing up in protoplanetary disks, stellar nurseries, and varying star-forming regions tweaked the pHs, mainly through temperature-dictating particle scale. There were studies suggesting radiation fields might alter sizes too, but after chatting with specialists, I suspect that's off base. Temperature's the key driver. Even without buying into the thick disk idea, it'd be great to pinpoint the originating temperature of this body, and I feel like we're closing in on that. Detecting PAH glow could help, and ALMA might catch some of that too. giving us a firmer grip. Lately, PAHs have been on my mind a ton. They're fascinating molecules, popping up everywhere in spectra, and we find traces in meteorites, solar system comets, that sort of thing. But crucially, they tie into carbon chemistry, which hints at life's beginnings. What might a PAH signature reveal about conditions in a distant star system, say an old one? Could the cosmos buzz with biology if PAHs blanket the void? PAHs stayed a total puzzle for years, and honestly, they still hold secrets. They turned up first much like helium did, spotted via odd spectral lines during a solar eclipse. Infrared observations flagged bizarre, unforeseen features with unknown sources, baffling experts for decades until we pinned it on PAHs. Quick primer for anyone with basic chem knowledge. A benzene ring is just 6 carbon atoms in a loop. PAHs build on that by chaining benzene rings into flat, carpet-like sheets. This setup lets the structure oscillate, the rings squash inward, or edges flap up and down. Think of tapping a drumhead. It ripples, producing waves. For PAHs, those motions generate spectral lines in the infrared, just like drum vibrations yield sounds. Especially when an ultraviolet photon from the sun or another star hits a PAH, it starts vibrating, and that vibration, kind of like an electromagnetic version of sound, produces infrared light that we can actually detect. I haven't come across any reports of spotting PAHs from Oumuamua yet, but PAHs themselves are everywhere in the cosmos. It looks like a huge chunk of the universe's carbon exists as these in interstellar space, forming these small clusters of pure carbon material, sometimes with extras like nitrogen mixed in, which alters their spectral signature for easier identification. You'll find them in areas where stars are being born, so they ought to show up on something we suspect is a planetary-like object such as Oumuamua. We've picked up traces in comets, and even in asteroid samples returned from space. I'm not sure about the moon. Its surface is pretty unforgiving, after all. PAHs can reveal details about the temperature where the object originated. That's precisely why I'm eager for us to detect PAH emissions from Oumuamua. We usually picture comets forming way out in the cold depths of space, at temperatures around 3 Kelvin or so. For something from cosmic noon, it'd be closer to 6 Kelvin. Not a huge jump, just a tad warmer, given a redshift of 2, or the equivalent. Current observations suggest Oumuamua formed at roughly 100 Kelvin, which is quite toasty for star-forming regions and aligns somewhat with origins in the early universe's peak activity. PAHs might help verify that. Their discovery would be a big deal. The other possibility is that it came from a typical thin disk star system, maybe just a fragment that formed nearer to its star. After all, we know some materials around the sun did that, and it likely happens in other stellar setups too. The chemical signatures could clarify this, and time will tell. This feels like a thrilling moment in astronomy, and I truly hope we spot those PAHs from it, so we can use the data to understand the conditions under which this thing took shape. Looking ahead, with the Vera C. Rubin Observatory gearing up to spot tons more of these visitors, how do we prepare? What steps can we take to station assets in position to snag the next Oumuamua or Borisov-like interloper when it swings by, ready to observe it up close? As Ian Fleming's Goldfinger line goes, once is happenstance, twice is coincidence, 3 times is enemy action. Well, this isn't any hostile plot, but after one such object, plenty wondered if they'd keep coming. Some expected a flood right away, though we haven't seen a bunch yet. But with 3 confirmed now, it's obvious we'll uncover many more, no doubt about it. The Rubin survey in the south, plus upgrades to northern sky watches, will deliver heaps of them. We absolutely need strategies for handling these discoveries. I've been pondering this a ton lately, since it's clear that these things pop up unexpectedly, and suddenly you're asking a spacecraft team, maybe overseeing a billion-dollar mission, to pivot and help out, like some Oliver Twist begging for seconds. They can't just drop everything without a framework. Something like the IAU or a similar body could set guidelines. These are the types of objects we'll encounter. Here's what observations make sense, and this is how to prioritize them. Take Oumuamua. It ended up on the sun's far side, so telescopes alone couldn't cut it. Spacecraft had to step up. You get just one chance with these, since they zip through and vanish. Whatever intel we miss is gone forever. No second chances, no do-overs. They're not going to show up on some predictable schedule or anything like that. So far, they've all been pretty varied. And, that pattern might stick around for a bit. Oh, and by the way, I've been pondering a ton about what 3i is showing us on a bigger scale when it comes to handling these fresh visitors from beyond our solar system. Like, Ian Fleming had his Goldfinger villain put it this way: once is happenstance, twice is coincidence, but 3 times? That's enemy action, or, in this case, a clear trend. We're definitely going to spot more of them. That's obvious now. After 1i, plenty of folks figured we'd have a bunch more zooming in, while others, me included, wondered if there'd be that many. We haven't caught another one yet. But hit 3 of these things, and boom, we're in for a bunch. Let me stress this strongly. With any of them, we've got just one shot. Take 3i, it's barreling through the solar system, and we can't halt it. Once it's gone, sure, way down the line, maybe we could launch a probe after it, like when we head out to Proxima Centauri or whatever. But in our lifetimes, probably not going to reach it. So, that's the deal. We take what observations we snag, and that's it. The key here is to grab every bit of info possible. That said, it's a big ask to hit up a spacecraft team out of nowhere and go, "Hey, check out this object, you gotta study it." Especially since they just happen to be positioned perfectly. That's tough. And honestly, it's a huge credit to folks like me, who basically popped up unexpectedly. Though I already knew some of these people, but still, no UN resolutions, no congressional mandates, no NASA boss issuing orders, or anything formal. It was just everyday people, in a manner of speaking, and I wasn't alone in pushing for this. We kept saying it had to happen, and gradually, ears perked up. It'd help if there was some system or framework in place for that. For instance, imagine another 3i, like thing swings by on the inner solar system side. What's the plan to rally all the deep space probes? Can we prioritize? These observations would be great, those are must-haves. And when I say we, I mean the whole community, not just chatting it out on YouTube or Facebook, probably. On the flip side, I wouldn't want to lock it down to waiting for IU votes or resolutions. That could drag on and might not pan out. Not sure. Actually, the next IU meeting's around the corner, and it'd be cool to hash this out there. How to establish priorities and all that. I do know it's helpful when scientists publish papers explaining why certain observations matter, how they tackle key questions. Operators really appreciate that. It lets them justify to their bosses, this isn't just for show or PR. Experts say it's valuable. So, yeah, I urge everyone to jot down those papers. We've got about 2 months, really, 2 solid months. Jump on it. If you think my take's off, write your own version. The more input, the better. Because whatever data we pull in is all we'll have. And I reckon people are catching on. Expect a flood of info from ground-based telescopes, Earth-orbiting satellites, and those far-out probes. Lots of surprise efforts and hard work poured in. My group, for one, dove in deep for over 6 weeks straight. That's intense for a total surprise. And get this, no budget for it either. It was just, we have to make this work, no ifs or buts. So, dive in and get it done. I'm super excited to see all the incoming data, and I'm thrilled to have chipped in, even if just a little, to make it real. I've got this nagging feeling I reckon this discovery really piqued the interest of plenty of skywatchers out there. It's tough to overlook something so captivating. In the most optimistic view, it could be a remnant from the universe's ancient past. On the flip side, even if we just rule out what it isn't, we'll gain fresh insights into visitors from beyond our solar system. This feels like the dawn of a thrilling era in research, especially now that we're spotting more of these things, just like you pointed out regarding Ian Fleming. Anyway, best of luck to you, and fingers crossed you'll join us again as we dive deeper into these cosmic wanderers. Appreciate it, Marshall. Thanks so much. Really grateful for the chat, and yeah, things are buzzing with excitement around here. Feels like an early holiday gift. I'm dying to unwrap what we find by December. You bet. Folks, check out the link in the description for Marshall and the team's article. Event Horizon, along with my channel, is now a podcast on Apple Podcasts, Spotify, and YouTube memberships. Get early access to episodes, extras, and chill-out material. Jump in today via the links below for your favorite spot. Heat. Heat. Music. Applause. Music. Heat. Heat. Music. Heat. Heat. Well, music, turn it.